we start part C, brute force method. Before we start this new topic, I want to complete one example we couldn't finish in part B. So in our C.1, more examples of asymptotic notations. Example number 8. Because it is too long, so we couldn't finish last time. So let's do it now. Yeah. All right. First, the question. Yeah. We already saw the question. We want to show that n factorial belongs to little o of n to the nth. This thing. But the hardest part is n factorial. How do you represent n factorial in a more user-friendly way? Yeah. So that's not easy. So we rely on a special formula, Stirling's formula, and we use the upper bound, lower bound version. Yeah. That approximate version, not very convenient to use here. So we use this upper bound, lower bound version. The question, how do we use it? Yeah. So you can see with this inequality, if we divide n to the nth both sides. Yeah, because if you look at our original question, we need to calculate the limit n factorial over n to the nth. So, and in the inequality, you can find n to the nth part, right? So then it's very easy. We can calculate n factorial over n to the nth using another two upper bound, lower bound functions to characterize, to represent. Yeah. So with that, so now we can calculate the limit in a very special way. So now, with upper bound, lower bound, now let us calculate the limit when n goes to infinity. The middle part, relatively hard to do it directly. So let's work on the upper bound part, lower bound part. That's not very hard to work. Why? Look at the variable part, the variable part. Okay, look at that part. It looks quite familiar to us, right? Yeah. Why? Because this is exponential function, right? So that is a power function. When you compare power function with exponential function, we did that before. We have some result. The exponential function increases much faster than a power function. So we can get the 0 here and also 0 right-hand side. Okay? I hope you can recall that part. Yeah. Here I just refer to our example number 5 in B.4. Number 5. In that one, we did this. N to the d, we only need the d positive. Any positive d. Okay? Although in that example, we use positive integer, but now you can see even d is not an integer, we can still do it. We can use the similar method, but we need to modify a little bit. Similar method. When you use the L'Hopital's rule, you need to modify our integer version slightly, then you can get the same result here. All right. With this, because the little here, little o, so that means the limit is 0, right? N to the d over a to the n. Here our a equals e, natural log base e. Our d equals 1/2, right? Square root. This limit equals 0. Little o tells us the limit is 0. With that, so you get both upper bound, lower bound side, the limit is 0. The limit is 0. Okay? Now, the conclusion. So here, before we make the conclusion, so I have to erase it. Before we make that conclusion, we use a theorem called a sandwich theorem or squeeze theorem. Both names, okay? So you just choose the one you like. Squeeze theorem or sandwich theorem. Squeeze, we have upper bound side, lower bound side, then we squeeze the middle part from two sides. Sandwich, the middle part, that's our targeting part, right? It is, sandwiched by upper bound, lower bound side, and we know the answer for the upper bound, lower bound. Then we can get the answer of the middle part. That's the theorem. So we get conclusion, the middle part of the limit is also 0. Upper bound limit 0, lower bound limit 0. In the middle must be 0. Right? Because the limit of the middle part, you cannot be greater than the upper bound limit, right? You cannot be smaller than the lower bound limit. You cannot be greater than 0. You cannot be less than 0. So you can only be 0. That logic, very simple. All right, so we get the answer. All right, so we show little o. After we get that 0 limit, that's the little o. Now, the last example of this example part. Last example. Multiple choice question. For each of the following functions, indicate the class big theta of g of m function. The function belongs to, use the simplest g of m possible in your answers. All right. So this question I select from our textbook. So A, this function, B, this square root function, C, a long log function, D, exponential function, 2 terms, E, floor function of log base 2 function. These 5 functions we want to, using the simplest possible growth g function to represent. All right, so here, let me do it one by one. For A, first, let's select the dominant term. Let us ignore the minor terms. So here, +1, the minor term. Let's ignore it. So after we ignore that +1, n squared, then you take 10th power, you get big theta of n to the 20th. That's simple. The simplest possible g function. N to the 20th, that's the simplest possible g function. All right, B, we take the, under the square root, we take the dominant term. So 10 n squared. Okay, minor term, ignore. Next step, the 10, it's a constant we can ignore. We only keep n squared. Okay, the n squared, after you take square root, you only have n left. So that's the simplest g function, big theta of n. All right, the next Next, I want to work on the simplest one first. So I do not have to follow the natural order. The simplest one, E is the simplest. Because the floor function, this part, if I remove the floor function, less than or equal to, actually less than, right? So less than plus 1, right? Less than the function, less than this function. We don't need a plus 1, right? Because the floor function, you can only be smaller than the original function, right? Smaller or equal to original function. So less than or equal to log base 2 of n. So we don't need the plus 1. Plus 1, that's for the ceiling function. So we will leave it to the ceiling function case. All right. So now this is the growth function, right? The growth function. All right. Then the base 2, the base number is not important. The base number is not important. The reason is there is a base change formula. If you know that base change formula, the base is not important. So this 2 here, so any, just a valid base, the base number is not important. We will see that base change formula soon. All right. The 2 terms, but the second term has larger base, 3. The larger base exponential function will dominate the smaller base exponential. So that means this is the dominant term. We just take this dominant term. Okay, big theta constant is not important. Minus 1, so that belongs to the constant part. So we only take the simplest possible, so we don't need a minus 1. Because minus 1, we can write as 1/3 times 3 to the nth. This is a constant, right? The constant C. The constant, when we consider a growth function, we can ignore the constant, right? We want to get the simplest possible growth function. So that's why 3 to the n, that's the simplest. Okay. All right. The last one, C option. So let's take a look. The dominant part. Log n plus 2 square by a property of log, that square we can move to the front. Multiplication. So that's a property. Okay? So that's a constant. So here, this 2 actually, you just move to the front as a constant. Okay? All right. The second one, you have this square, you cannot move because it's not inside a log function. You cannot move it to anywhere. All right. But the log n over 2 by the log property, log of n minus 1. Division, we can change to subtraction by logarithm property. All right. And this is a minor term, right? We can ignore. All right. So you can see, too messy here. I have to erase some part. Too messy. All right. Now the C part, you can see the dominant term is, the second term is dominant. Second term, because the squared part dominate that part, polynomial part. The log part, the same, right? That square you move 2 to the front as a constant. So the log part, they are the same, but the polynomial part, the second one higher than the first one. So this is the dominant term. Now, when we consider growth function, the simplest possible growth function, we ignore the minor part. Plus 2 minor, we ignore. Divided by 2 minor, we ignore. So the answer, let me show the answer. Answer, big theta of n squared times log n. See, the simplest possible g of n. Okay, all right, so hope you get all these things. Yeah, so I go through a little fast. So hope you can get everything I explained here. Yeah. At the end, just a review, the change of base rule of logarithm function, this one. Initially, suppose you have base A, right? Base A of log B. But now you feel you like to change to a different base. Then you have this formula. Numerator, it is a fraction. The numerator, you use base C, apply log function on B. Then denominator, the same base C, you apply the log function on A. Then you take the ratio. Yeah. Here I just review a little bit. Yeah. Change of base rule. So later, after I give you here, later in several situations, I will use this formula directly. Okay. All right, so let's stop the C.1 video right here.